Many people involved with data science know about descriptive statistics. It's a way of looking at data and getting things like the median, for example, or outliers, or the min or the max. You can also do similar things with graphs, which have very different metrics. In this case, we're going to look at centrality. And in fact, we're going to look at something called closeness centrality, which is a measure that indicates the average distance between a node and all the other nodes in the network. In this case, I'm going to make it kind of fun and use the UFC here, and it's going to be able to provide insights about a fighter's engagement with others. And the distance is the shortest path between two nodes. So in this context, the number of fights between two fighters. So let's go ahead and take a look at this library first here. It's called petgraph. And if I go over to cargo, you can see I've got this imported. Now, if we take a look at next here, I defined a struct. And this can be a little bit confusing at first when you see something like a struct and this implementation here as well. But it's actually identical to the Python code as follows, right? If you're going to add, a name attribute to an object in Python, it's similar here. I'm adding the fighter name. Now, I also want to have some display things that I'll do as well. Then I have some code that adds the edge. So in this case, it's able to add that to the graph. And then finally, I put it all together. So in this case, we've got a main function. I create a mutable graph data structure here, and then I add the fighters inside. So these are very popular UFC fighters: Dustin Poirier, Khabib, Jose Aldo, Conor McGregor, Nate Diaz. These are all people that have some relationship in terms of fighting. I then go through and I iterate on them and add them to the nodes, and then I add the relationship. So in this case, again, this would be similar to any kind of network analysis involving social media or real world relationships. We have Dustin Poirier versus Khabib. That was one UFC fight. There's also Khabib versus Conor, Conor versus Dustin, Conor versus Jose, Conor versus Nate, Dustin versus Nate, Jose versus Nate. So we have these relationships defined right here. And then this particular for loop, what it does is it figures out the name, the degree, the closeness, and then prints out the closeness centrality. Now I go through and I add some explanations here as well. So again, if you're a data engineer, machine learning engineer, data scientist, this could be something that would be very common. If you were going to create, let's say, a custom metric or a chart, in this case, I match on the word Conor McGregor, and we can see that he's going to have the lowest centrality because he's fought with the other fighters, et cetera, et cetera. So I print out the explanations based on the centrality score. So let's go ahead and run this to see it actually in action. So if I type in cargo run, it's going to go through and it's going to print out the results. So if we go through here, we can see that the closeness centrality of Dustin Poirier is 0.33. But if we look at the highest here, which is Conor McGregor, he has the lowest centrality. So it's 0.25. Now, the reason why his centrality is the lowest, it means that he's fought with all of the other fighters in the network. And so a lower centrality means a higher number of fights. So this is really the best score here in terms of the people in this particular relationship. We can see that the worst score is Khabib and Jose Aldo. And you can see here that they both have a 0.5. So kind of double the score of Conor McGregor. And then we see that Dustin and Nate are equally tied for second place here. So this is a great way to figure out custom metrics that are really unique to either in-world relationships or sports relationships or social networks. And of course, you can do it very easily with Rust. All right, in this video, I have a simple Rust program that generates a list of 100 random fruits and calculates the number of unique fruits we end up with. So let's go ahead and take a look at the very beginning here. One of the key takeaways as well is I'm using the rand external crate here to help me out. And in particular, the sequence slice random and thread RNG here are doing a lot of the heavy lifting because they'll generate a random choice from a list of fruits. And a lot of times this is a great way to generate random choices is, in this case, this is a vector, and I'm going to feed it into the random selections from the rand crate. Now we're going to use a hash set from the standard library collection as well. So that's another thing to pay attention to. And one of the key properties of a hash set is that it will only store unique elements. So this is perfect for this kind of use case. And then if we scroll down here a little bit, again, this is the random stuff that we actually have some code here that allows us to, generate a fruit. So in this case, we go through here and we have a fruit set, and we say for basically 100 fruits here, let's go ahead and generate the fruit. Now, again, this is the function that does all of the heavy lifting here. Now let's go ahead and run the code. I'm going to type in cargo run, and you'll see here it compiles, and then I've been able to generate 100 random fruits, and the number of unique fruits generated is 8. Now, just because we generated 100 fruits, the number of unique fruits is fewer because it's possible to select the same fruit more than once, right? That's really the key takeaway here, even though this is 8. Now, if I changed it, for example, to let's say 10, this could be kind of interesting because the fact of randomness here, it would potentially change things a little bit and allow us to maybe see what would happen where many scenarios there won't be 8 random fruits. Let's go ahead and run it. There we go. Look, in this case, 6, even though I generated 10, I run it again, 4, right? So because of randomness here, it's not always going to get to 10. In fact, it would be uh, not that common to get to 10 random fruits. It's possible that each one could be uniquely selected, but then you're getting into a mathematical combination, and you'd have to figure that out. But in this particular scenario here, again, if I go back to 100, 100, we can actually see it again, and we're able to see this random fruit generator. So really, the randomness plus the hash set in general are really good skills to know, and it's pretty straightforward to do this with Rust. And again, one of the nice things about Rust is that it's a compiled language and it has lots of safety features. And I could generate something like this, for example, find all the unique customers, and this could be a dashboard or some kind of utility for a data engineer. Okay, let's dive into another fun data structure, which is B tree sets. And in this Rust program, it's going to generate a B tree set of fruit with varying amounts. So the B tree set is another unique collection that's a similar collection to a hash set, but it keeps its elements in a sorted order, which could be really helpful for certain kinds of data engineering problems. If you wanted to, again, collect some custom metrics. So first step, we are using the random crate here. How do I know? I could just go to cargo. That's one of the nice things about a Rust project. Really simple to understand what's being used. Now, the other thing we're going to do is we're going to use these random features here. So slice, random, thread, RNG, and then we're going to define a list of fruits. So again, pretty simple to use a vector here. The vector is going to contain strings. I think this is something that's really powerful about Rust is that it's going to explicitly tell you what's going on. So in this case, we know it's a vector and the vector has strings inside. So we don't have to guess like what else is going to be inside of this vector. Well, it's a vector and it's got strings inside. And here we also have the amounts here, and we also have the randomness that comes through here. So this is where the shuffling occurs. Now, finally here, what we do is we actually keep track of the amount of fruits here as well. And then at the very end, we actually are able to calculate, a fruit set. So let's go ahead and do this. So when I go ahead and type in cargo run, it's going to build it. And we see we've got the first one has a fig, and then we have 3 as banana, date, and grape. The next one has banana, maturity, date, elderberry, fig. The next one is apple, banana, date, elderberry, fig, grape, honeydew, etc. Right. So the idea here is that it's creating these unique sets and it's preserving the order at the same time, which again is really powerful because depending on what kind of problem you're solving, maybe shopping cart transactions or some kind of, really fancy statistic that you want to put into a dashboard. This is an elegant data structure for that. With Rust, and of course, because it has binary-based deployment, it would be very easy to package this up and put it somewhere, and it would run extremely efficiently at scale with C-level type performance. All right, in this video, I'm gonna make a Rust program that creates a fruit salad, but it has a twist here in that I'm going to assign the fruit fig, which is one of my favorite fruits, the priority. And this program uses the binary heap to accomplish this. And the Rust standard library is able to actually build this for us, which is nice. Binary heap comes from standard library collections. And the first thing that we're going to take a look at is there's an enum here, which is a fig and other. And then in this particular scenario here, I'm going to define figs as the highest priority by implementing ORD. So I say implement ORD. So basically make the order here. And I'm going to say that basically figs here are going to be at the top and then other fruits are going to be at the bottom here. And then I also have partial order as well. And then finally, I get into the generation of the fruit salad. So what I do is I then use that data structure. I use some randomness as well. And I say, look, here's my fruits: apple, orange, pear, peach, banana, fig, 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 fig. All right. So I just added a few figs here to kind of make the stack a little bit more oriented to figs. And then what I say is, here's the fruit salad. Let's go ahead and say that I'm going to start with a fig count. And I'm going to say, while figs are under 2, go ahead and keep selecting fruit. So I'm going to prioritize for figs, but I'm also going to stack the deck in the favor of the figs as well. And what's going to happen is it's going to push things down here until I've got a couple figs, and then it's going to generate the rest of our fruit salad here. So let's go ahead and run this and take a look at how it works. We go ahead and say cargo run. We can see that the random fruit salad with 2 servings of figs, we have peach, peach, orange, apple, orange, fig, fig. You run it again, you'll see there's always going to be a couple figs here, which is pretty neat. And it allows us to create this really kind of customized metric, which again is really useful for people that are doing good engineering. And the main thing to be considered about a binary heap is that it's a priority queue in Rust, and it's a very handy data structure when you need to constantly pull out the highest or the lowest value from a set. And that's it for this particular demo. Go ahead and try it out yourself.